Therefore, and what? Yesterday we talked about linear equations and their properties, kind of how to work with them. And so today we're talking about systems of equations. And you might recall from your studies of systems of equations in algebra that you learned how to work with systems of two equations and systems of three equations. For example, you had something like this. As usual. Forget to adjust the size of the pen. I don't like it that thick. So for example, to solve the system, something like this, you had and something like that, or something where you had three equations. You may remember these from your Algebra 2 classes. I'm not actually going to sit and solve this, but you may recall that you did some of these from your algebra classes, something similar to this. And in general, it will be very similar to this in this section. So today we're talking about systems of equations. Okay. And a simple definition of a system to give you to work with is collection of two or more equations. Okay, the simple one to work with. Two or more equations, right? The system. So you can have 3, you can have 4, you can have 10 for all I care. The system of two or more equations. Your textbook defines it to be, you can have an equation you can have m for your number of equations, you can have n for your number of variables. Of course, n must be greater than 1. Okay. Now, n must be greater than 1, and an element of integers that are positive. You can't have half an equation, obviously. So извините меня, пожалуйста. Okay. Okay. Now, with our number of variables, it doesn't matter. However, we have to have at least two variables, right? So we have to have at least two variables in an equation. So and obviously, since you can't have half variables, it also must be an element of z positive, which z is representative of integers. And now, we know, how do we know about the solutions to these equations? Of course, the number of equations dictates the number of variables that you need to solve the problem. Okay. To solve the problem. So if you have three equations, you need three variables. If you have five equations, you need five variables. You can have less, you can have more. However, if you have you can have less, you can have more. However, there's certain dictates that happen when this happens. So I will write them down right here for you. And so if n is less than m, meaning the number of variables, that implies that sum it implies that some of the equations become redundant. That is to say, that eventually, by the time you combine them all together, right, is that one of the equations will cancel. Okay? That has to happen. Why? There's not enough to work with. You don't have enough equations to work with. Simple. There's not enough variables to work with. Okay. If there's not enough variables to work with in this situation. So an example of that would be something like this. Let's say I have like Right. In this situation, I have 3 equations, but I only have two variables to work with. Right? I can get rid of one equation and simply eliminate it into 2 and then work with that. Okay. That's what I mean by one of the equations. What I mean by one of the equations becoming redundant is that you can basically combine it into one of the other equations, and you can work with it that way. It's still solvable, but in other words, what I'm saying is that you overwrote the equation. You gave yourself too much information. That's what happened. Okay. In this situation, you give yourself too much information, so we combine it into one equation, and then we can work that way. And in this situation, you probably combine equation 1 with equation 3, and you could simply solve it that way. Now, we'll talk about how to solve these in a little bit here. We have another possible situation. If n, the number of variables, is greater than the number of equations you have, then variables, if n is greater than m, so if the number of variables is greater than the number of equations, then your variables must be defined as parameters. Okay. So, in other words, what will happen, you'll have an infinite number of solutions, and we'll talk about how that occurs in a minute here. So, an example of this say something like this. Okay, something like that. In this situation, you have to define an equation as a parameter. You would actually have to solve for one of the variables and then define it as a parameter. So, but we'll go into detail on how to do that in a bit. Okay. So now that we've gone over the possible situations, let's go over how we find solutions to this equation. So we asked the question, how do we find solutions? Well, first we need to figure out a definition of solution that we can work with. Okay. A solution to a linear equation, they give you some fancy variable here. Okay. They give you some fancy verbiage, but basically, to translate what the hell it means, a solution satisfies all equations in a system. So solutions to yeah, that's an ugly all. So a solution satisfies all the equations that are set in a system, basically. Simply done. Now, you'll recall, of course, the types of solutions that are possible. Okay. Right. You'll recall these definitions from algebra. You'll recall what a consistent solution is. You'll recall recall these terms consistent and inconsistent. Of course, consistent is when system has a solution and then inconsistent is, of course, when the system does not have a solution. Now, visually, to visualize this concept, okay, what do I mean by that? Okay, you'll recall from 2 and 3 dimensions that you had planes, you have lines and planes. So when n equals 2, you have a line, and when n equals 3, you have a plane. Okay, so you'll recall the way this is possible. So with lines, let's go to a new page actually. With lines, you can have them be parallel, which is of course inconsistent. Which is inconsistent because there's nowhere to intersect. And because they don't intersect, there's no solution. You can also have them intersect at one point. Okay. In this situation where they intersect, which is consistent. Okay. This is consistent because it has a solution. Okay. Part 3 is, of course, where they coincide. And it is consistent in infinitely many solutions. Okay. And this is all review from, of course, algebra, which you learned hundreds of years ago, right? And I can't draw, so you'll just have to bear with it. Okay, you have 2 lines there. This is all review. And for planes, the same principle applies, but we can speak of it a little bit differently. And because planes are 3-dimensional figures, we can have a concept to work with. Here. Right? They can intersect. Planes can be parallel. I can't draw, so you just have to bear with these horrible drawings once again. So in this situation, they intersect at no points. They are parallel, right? And so this is inconsistent. Your book does not have all of these drawings, but I'm putting them all in, right? The planes can be skewed. They don't have to intersect. The planes can be skewed, meaning it's also inconsistent. Neither. Showing that it goes under, not it's going underneath. This is also inconsistent. These are skew planes. And of course, lastly, you can have them intersect. You can have them intersect at 1 point, 2 points, or 3 points. Okay. I've got to be the worst artist in history. So, and the point where or the line where they all intersect is, of course, the solution to the problem. This is at 1 point. Intersect at 1 point in this. You can make them intersect at 2 points, and you can make them intersect at 3 points as well. Or at one line, to be more specific, actually. Okay. And so and then here you see lines forming at 2 points. Okay. So this situation you intersect at 2 points. And of course they can intersect at 3 lines, and this will be consistent. They can intersect at 3. Okay. And 4 is, of course, when they intersect at 3 points. Right, so we have 3 points of intersection. So let me get my red out. I apologize for such a bad drawing here, but you just have to bear with it. Okay. This is also consistent, but with 3 lines as a solution or a point. You can have a point, a line, or a plane as a solution in with 3 equations. Now, with 3 variables. So, and then as you get to more figures, more variables, you can't necessarily geometrically represent them, but the concept is similar. We speak of algebraic structure. And when we speak of an algebraic structure, we refer to anything with 4 or more variables. We refer, I will call it that. So, is of course the geometric. And is 4 or greater, and is greater than 4 variables. So, okay. Oh, oops, that's a horrible line, but it'll have to do. Okay. Actually, no, it won't. Okay, an algebraic structure refers to the geometric solution, okay, of n of 4 or more variables. Good God, this pen is not cooperating today. Okay. There you go. N is 4 or more variables. Okay. Algebraic structure, you got it. So, and so your textbook gives you fancy definition of, not a definition, but they'll show you what a general system looks like. So a system in n variables with we have x sub 1 2 plus the dot. N is equal to b sub 1 and then excuse me. Yeah. So this is what our n excuse me. This is what our systems of equations look like. Okay. As you recall, that there are coefficients when we have systems of equations, we can have coefficients, which is just any real number being multiplied next to a variable. Excuse me. Okay. So, and of course, to solve these, we do back substitution. We have back substitution, and of course, we'll learn matrices. How to deal with matrices in the next section. Извините меня, пожалуйста. Now, excuse me. Apologize. So, we all these have different methods of solving equations, back substitution. You can use matrices. You learn all this during Algebra 2. And I'll happily go over it again in the next section. So solve it, you of course don't remember the Yes, we need to. Yeah, excuse me. Be right back. Sorry about that. So, we have the elementary row operations. That we have what we call the elementary row operations, which of course things that we're allowed to do to help us find a solution. Excuse me while I battle the sneezes. Okay. So, okay, better. Okay. Okay. So the elementary row operations, I'll write them down. We may switch. Excuse me. We may switch any two rows. Excuse me. We may multiply. We multiply. We multiply by a non-zero. Any row. And of course, lastly, 3. We may add any two rows together. You can add a constant multiple. And of course, we can add. And of course, I'll write it here, even though it's not in the book. Of course, we may add equations together. Okay. Now, excuse me. Alright, so let's stop yapping here, and then we'll continue to talk about systems of equations in the next video here, and we'll continue by solving some systems of equations.